But I want to spend a little bit of time talking about a couple of weird bugs that affected, frankly, all of us earlier this year, and walk you through the inside story of how we mitigated those bugs at DigitalOcean. And on the side, we're going to do a little bit of multiverse traveling, which will be at least entertaining. I don't know. We'll see how it goes. So let's get started. Spectre and Meltdown, in fact, they actually have logos, which is convenient. Meltdown is an appropriate sort of shield that's melting, and Spectre is a ghost with a stick. Because, a ghost isn't scary enough. A ghost with a stick really scares you a little bit more. But they are two new significant security bugs that have affected the whole world of computing. Now, think about that for a moment. The whole world. Everybody sitting in this room was affected by these bugs. Everybody you know was affected by these bugs. Every cloud provider, every software as a service provider, anybody running a computer since 1995, which, frankly, I was just out of high school, was affected by these bugs. And so, at best, you had to reboot your computer to get the patches you needed. And it happened overnight, perhaps, if it's a Windows machine, or if it's a Mac. It happened right now. Anyway, Mac's kind of aggressive on their updates. But the bottom line is that you just transparently got your updates. In the case of a cloud provider, though, or a software as a service provider, things were not quite as fun. We had to go out and compile kernels by hand. We had to track down patches on the kernel mailing list without a whole lot of information about what patches we were even looking for. We had to compile our own kernel, validate it on our different generations of hardware. Then we had to roll it out to tens of thousands of machines. And to make things even more fun, we had to reboot all 10,000, 20,000 machines so that those patches could be applied. And in the process, we affected millions of customers with this process. So my name is Dave Smith. I am the VP of Engineering at DigitalOcean. And today I want to tell you sort of that inside story of what happened. And I want to tell it as seen from inside of DO. DigitalOcean I often call DO, so if I call it that during the presentation, that's why. But I want to tell you that inside story. And I also, in the process of telling you that story, am going to branch the timeline a little bit and say, here's what would have happened if we had been in a fully serverless environment. Because this is about serverless, after all. So the question is how would we deal with bugs of this magnitude in a serverless environment? We're going to cover a lot of ground. I'm going to make an attempt at explaining these bugs a little bit so that you can understand sort of why they're so pernicious and why this is such a big deal. We're going to dive pretty deep into modern processor architecture. I'm not going to spend a lot of time there, but you've got to sort of have a feel for that. So let's take a little detour. From a programming standpoint, we normally think about processors as doing one thing at a time. And the reality, though, is that they take time to load instructions. It's not like they just are able to execute an instruction right away. It takes time to load the instruction from memory, to actually execute the instruction, and then to save the results off, reset registers, yada, yada. And the other thing that processors spend a lot of time waiting for is electrons to settle down. Those electrons get really excited inside those processors. So we've got to let them settle down a little bit. So what this means is that, we've got to have some mechanism for keeping things moving. We don't just want to do one instruction at a time. We want to have as many instructions in flight at once, because the more instructions that are being processed at once, the faster the processor is. And so as a result, we got this concept of a pipeline. So most modern processors have the concept of an instruction pipeline. And usually they have actually multiple pipelines. So this way, they can do more stuff because you spend less time waiting. So more instructions per second, less time waiting. Everybody with me so far? All right. Nobody's yelling at me. That's good. So that brings us to speculative execution. And pipelines are most effective when there are no alternate code paths. In other words, when the instructions have no dependencies on each other, and the processor can just say, yep, I'm adding that number for you. Yep, I'm storing that number for you. Yep, I'm swapping these registers. As long as there's no dependencies between instructions, those pipelines, they fly. But the problem is a lot of the code that we write is not like that, right? Like, we all use if statements. Anybody here never used an if statement? I'd love to meet you. OK. We all use a lot of if statements. We all use for loops, while loops. Anything that has any sort of conditional or branch is going to affect this pipeline. And so this concept of speculative execution is that this is a way to speed up these alternate code paths. This is an interesting thing for us because these processor designers, when they realize that, hey, we fill up this pipeline and then you hit a branch and we have to flush the whole pipeline, we have to throw away all the instructions because this branch changed the direction of the code path, they said, you know what? What if we just made a guess? What if we just said, OK, look, actually evaluating the conditional is going to take a few seconds, well, microseconds or whatever. And what we're going to do in the meantime is we're just going to go ahead and run all that other code behind it. Because that way, when the conditional actually executes, hey, we've already saved you some time and we've sped stuff up. So that's what they did. And the problem is that most code has tons of different paths that makes this pipeline inefficient, and we can make these guesses, if the slide will update, about the next path, and thereby speed up the processor again. So at this point, your processor is actually being fast by making random guesses. Isn't that fun? It's so much fun. So what's happening is that we're just relying on statistics that most times we can make a pretty good guess about which branch of path, and we avoid flushing the pipeline, thereby the pipeline runs faster. Now at this point, you're like, Dizzy, it is 4 in the afternoon. Why are you talking about this? Well, we need to understand speculation and speculative execution, because that guessing, that's the speculative execution. We're just going to kind of guess there. So here's the thing, though. If the speculation fails, we got to go back and clean things up, right? So it's great. The processor's making guesses, running instructions for us, speeding things up. But the problem is sometimes it's wrong. Sometimes it makes a guess and it's the wrong guess. And it doesn't even have to be that often, and we have to do all this work to clean up. And the problem with cleaning up is that the act of speculation has side effects. So just by executing, and I got to say, like, sometimes this feels like kind of a metaphysical argument here, but it's almost like by doing something speculatively, we have changed the world. So we can undo those actions, but we have already changed the world. Anyway, sorry, I'm digressing into metaphysics. But that's really what's going on here, is that we have these side effects. And the thing about Meltdown and Spectre is that even if the speculation is reverted, the side effects may have been able to be measured by a careful observer. That is a scary thing. That means that there is no real undo button, because we've moved electrons around on silicon. We've changed the world. Some quantum people would argue we've already forked into a multiverse at that point, right? Anyway, that was funnier in my head. So we know now that speculative execution is a way to speed things up, but when it's wrong, there's leftover side effects which we can look at if we are a careful observer. So let's talk about Meltdown. And Meltdown is a specific attack, right? Like, it's a very specific way of using these side effects of speculation to read arbitrary kernel memory. Now, the problem is, security of any modern operating system is dependent on this whole idea that one process can't read another process's memory. So obviously, if there is a way to get around this using speculative execution and side effects, that's a bad thing. And Meltdown uses these side effects from speculative execution to read arbitrary kernel memory. That means that one process can read any other process's memory. And in turn, on a hypervisor, one VM can read any other VM's memory. Now, I work for a cloud provider, and there's actually a lot of cloud providers out there. And our whole business model is built on the idea we have one physical computer that we share amongst a whole bunch of people. And the idea is that they don't know that each other is there. So anything like Meltdown, which melts boundaries, we don't tend to like these things. It's kind of a problem. So that's Meltdown as a concept. And it was a very significant concern. This idea that anybody could stand up a VM, run a little bit of code, and suddenly see all the other VMs running on the physical hardware, it's a scary thing. Anybody not find that scary? Is it just me? I mean, it could just be me. All right. So let's talk about Spectre. And I promise you, we will get to the story part of this, but you kind of got to understand some of the background here. Now, Spectre is a class of attacks, which is my guess as to why they gave the ghost a stick, because it's not just that the ghost scares you, it also hits you over the head with the stick. So it's kind of a whole class of attacks. And in this particular case, again, it uses speculative execution to trick a program into running code that it wouldn't normally. So the problem here is that speculative execution breaks our normal concept of correct programming. In other words, because the speculative execution engine is running pieces of code out of order than the order you wrote it in, you can't always guarantee what's going to happen. So Spectre used this to induce an analyzed program, and that's a key word there, an analyzed program, into executing code that under normal circumstances, the circumstances in which you wrote it, it would have never run. So what this means is that, consider for an example, you write a program that does an authorization check, right? So it does an authorization check and then does some computation on that after that authorization check. In a speculative execution world, what actually happens is that it sees the authorization check, it sees the computation code after it, the processor. The processor says, well, you know what, I think this authorization check is going to pass, because 99 out of 100 times it did before. So it runs the code that comes after the authorization check while the authorization check is completing. Whoa, like, I didn't want that code to run then. The processor's like, I'm just making things fast, man. Don't mess with me. But what happens then is that the authorization check kicks in, and then that code is rolled back, right? Like, that's the concept. But the problem is that there have been side effects from running that computational code. And if you're a careful observer, you can see that. And so, of course, there's a couple of things about Spectre is that it's much more time-consuming and targeted than Meltdown. Where Meltdown, you can just poke a couple of registers in careful ways, and hey, presto, you can read everybody's memory. In Spectre and Meltdown, in Spectre, you have to be a lot more thoughtful. You have to analyze the program. You have to attack it. You have to kind of trick it into doing some speculative execution. But if you do it, you can bypass very correct code and get it to tell you things it would have never told you. It's a very pernicious sort of attack. So, come on. Did that go? There we go. Fixing the problem. Well, it should be easy to fix this, right? Let's just disable speculative execution. Seems simple enough to me. Let's just turn that feature off, then it won't be a problem. Well, let me ask you, has anyone here ever used a Pentium Pro? Okay, a couple of hands here and there. How would you like to go back to that today? Because that's what would happen if we disable speculative execution. All right, now, the reality is that technology's advanced quite a ways. It probably wouldn't be that bad, but it wouldn't be good. It would be like going back 20+ years in processor speeds. One humorous note here. The initial advisory from CERT about these two bugs after it got out of the embargo was that, well, just replace your CPU, that'll solve your problem. The register put it more adeptly, I thought. They said, throw out your computer. Neither of these are actually fixes for these kinds of bugs. And the reality is that we are going to need to, yay. Come on. We're going to need to disable selectively, with really careful choices, the speculative execution engine, so that at certain key points in the kernel, in the microcode, we'll turn that off so that an attacker can't take advantage of it. And in order to do that, though, we're talking about a lot of different pieces. We're talking about fixing the microcode. I don't know if anyone knows, not many people know this, but there's actually another layer of software below your kernel, before the hardware, called microcode that actually runs on the processor. Nobody really knows how this works, because that's the domain of the chip vendor, Intel or AMD or whomever. But they can actually update that on the fly and change the way the processor behaves. So fixing Spectre and Meltdown actually require changes to that microcode. It requires changes to the kernel. It requires changes, if you're a cloud provider, to your emulation software. It requires changes to the kernel of the customer running in the emulator. It requires changes to anything that they use on top of it. we're talking now about a lot of changes to fix these bugs. These are not easy things to fix. And that's why I wanted to spend a little bit of time talking about them. Because this kind of gives us our first clue about serverless, right? Fixing Spectre and Meltdown is going to require key changes all the way down to the metal. There is no easy fix here. And serverless now enables this concept of scale out. But more importantly, and I made up a word because, hey, when you give a talk, you get to make up words, called scale refresh. Serverless enables us to not just scale out, but also do a scale refresh, which is where the cloud provider or the serverless provider changes out things underneath you in a transparent way, where you never even know about it, and it's a seamless experience. So that's one reason why serverless would be very attractive and why we're going to explore that other timeline. But in addition, in a serverless environment, we typically have concentrated state, sort of like Erica was talking about today. There's still state, it just tends to get moved around and put in different places. And curiously, it tends to be more concentrated. And so that means that if we're going to update stuff, we know where the boundaries of state are so that we can go slow in those areas and fast in areas where statelessness is in effect. Again, in a traditional setting, like the cloud provider is going to wind up updating many, many layers of software to address this. And probably the biggest setback or challenge with some of the Spectre Meltdown stuff is even when the cloud providers fixed it, even when DigitalOcean fixed it, we still had to have our customers fix it in their VMs as well. And there's no way for us to enforce that. And in a serverless environment, that wouldn't have been a problem. So let's briefly recap the situation, and then we'll talk a little bit about the timeline. Spectre and Meltdown represent a fundamental threat. They mean that clouds suddenly become porous. Anybody can hop on a cloud and see anything and everything. Fixes, in order to fix these things, we're going to need to apply fixes across a large swath of the stack. This is not an easy thing to do. And serverless has some properties that would have changed this situation dramatically. And as you'll see, as we go down sort of the multiverse and explore an alternate universe in terms of what it would have been like, it could have saved us a significant amount of time, but also it would have saved us a lot of customer impact. So for the purpose of this presentation, I'm going to assume that there is an alternate world of serverless, where DigitalOcean provides only a serverless environment. And it's going to have three major pieces. It's going to have functions as a service, Kubernetes as a service, and database as a service. Now, I know. Kubernetes as a service is arguably not serverless. It's got containers. You're not supposed to expose containers. But I think it actually speaks to the reality of the world we live in, that migrating systems over to serverless is going to require some compromises. And Kubernetes actually is a reasonable step in the right direction there. So let's go ahead and move into the timeline. January 1st is when things first started happening for DigitalOcean and every other cloud provider out there. We noticed this interesting blog post that started making the rounds by a person known as Python Sweetness. And this blog entry was very interesting because it said a couple of things. It said, there is an embargoed security bug that's out there. It theorized that this embargoed secret bug impacted any CPU that uses virtual memory. Now, if you know anything about CPUs, it's that they all use virtual memory, which is kind of a, whoa, that's a lot of CPUs. And to make matters even worse, it would require hardware changes to fix. Well, I mean, I don't know about you, but I've got 20,000 servers in data centers across the world. I can't just pull all the CPUs out very easily. It's not something that we do on a regular basis. And what's more is that the patches to address some of these things had the potential for huge performance impacts. Some people, the initial estimates were 10 to 40% hit on any I/O operation. 10 to 40%. That is, I think, somewhere like 5 to 6 years of processor evolution that we would be taking a step back if those numbers turned out to be true. So we noticed this. I had a conversation with the team that manages our hypervisors, a really brilliant engineering manager and software engineer that's our tech lead, and said, hey, we need to look into this. Like, I don't know how real this thing is because it sounds a little hyperbolic, but, we should be thorough. But it was, it's January 1st. It's a new year. Everybody's kind of like, it's a new year. This is going to be a great year. Well, that wasn't true. January 2nd, one day into the event, the Register article comes out, and things really start to look serious now. Because that Register article had a proof of concept in it for what we would later know to be Meltdown. And it looks like, at the time, that this is a huge, like drive a truck through it, Intel bug. Now, what we later found out, of course, is that Meltdown was a variant, and that variant was specific to Intel, but it was also found on other processor architectures as well. And there were starting to be rumblings of absolutely huge performance impacts to any sort of I/O load. But ultimately, there was just a lot of confusion. But that proof of concept got a lot of people's attention. And the proof of concept showed this. It showed someone starting a process and then starting to read off private keys from various places in kernel memory. That is alarming. At this point, everybody's reaching out to Intel, everybody's reaching out to their vendors, like, what is going on? Because that is a scary thing right there. And later on, of course, we would find that there was actually a variety of bugs around speculative execution. And that takes us to day 3. And this is, at this point, the embargo has broken. And Google Zero, which is the project that actually discovered these variants, go ahead and release their blog post. And they revealed for the first time the name and the natures of these bugs. And a few key things became clear. There wasn't one bug. There was 3 of them. And Meltdown was the worst, but Spectre was also really not bad. Or it was really bad. That was just a Freudian slip there. I really didn't want it to be bad. What's more, there had been a very secretive, very tight embargo on this information for 6 months amongst about 5 super large tech companies. So yes, this was January 3rd. We were just finding out about this, as was every other cloud provider, except for a couple of them. I don't need to name names here. It should be really clear. But the reality is that we and other cloud providers caught a lot of heat for like, why aren't you guys fixing this sooner? It looks like these other big cloud providers have been on top of this. And it's like, well, yeah, they had inside information 6 months ago. So this is our story of what happened. And to be clear, anyone not in the embargo, which was everyone was not in the embargo, only a couple of people were, was going to have a really fun time. And by fun, I mean not fun, trying to solve these problems, while the biggest companies had a 6-month lead on it already. This was also the point where we became certain, as did every other cloud provider, that we would be rebooting the fleet. Now, rebooting the fleet might sound like, well, okay, Dizzy, you just get everybody from DigitalOcean to go to the data centers and turn things off and on. What's so hard about this? A little more involved than that, as you'll find out. And in no small part because we didn't even know at this point what kernel patches we needed, what microcode updates we needed. In fact, their microcode wasn't even released yet. Take it forward to January 4th, 3 days in. Now, you can sort of see we're 4 days into the year, and things are developing very rapidly at this point. At this point, Dio already has probably, a team of 10 working around the clock trying to dig into these bugs, understand the kernel impact, stuff like that. So we get some good news, though. And the news is that the confirmation that KVM, which is a virtualization layer that DigitalOcean uses, is immune to Meltdown. Now, this is a huge break for us, because a lot of the other vendors, including the ones in the embargo, had been using something called Zen, which actually was very susceptible to Meltdown. And as a result, they had to fix those problems. In our particular case, we were immune to Meltdown. We didn't even have to worry about that one. So Spectre was the one we had to worry about. But this is good, because at this point, nobody knows how to fix Spectre. There's like a bunch of different ideas out there about how we're going to do this, but nobody really knows. So we know we've got time to sort of do the right thing here. We also start to get claims now that vendors are going to be releasing their patches on January 9th. But our own research is raising some big questions about that, so we start researching and putting together our own kernel from scratch. And at this point, 4 days in, we had some really naive hopes that we could reboot the fleet in a week. That didn't happen. January 5th, T+4, we've got the plans starting to come together. We realized that in order to reboot the fleet, it's not enough just to send everybody to data centers and push buttons. We actually need to write a bunch of software to automate the fleet reboot, which is a big deal. And we also realized that we're going to need to start investigating our entire product line, because if it really is a 10 to 40% hit on any I/O things, that means our block storage product is vulnerable. That means our load balancers are vulnerable. Everything needs to be retested with whatever kernel patches we can find to understand the impact. January 9th, this is when the vendors were supposed to release their patches. There were no vendor patches. No big surprise there. We do complete the first boot of a patched kernel, which is very exciting for us. But we start to realize that there's going to be a lot of internal systems we have to upgrade. We're going to need to run at 100x our design spec in order to reboot the fleet in a timely manner. Now, on a daily basis, we have hardware all over the fleet, right? You run enough computers, you start getting failures. It's just a law of statistics. But when you're talking about rebooting all of the computers in rapid succession, your failure rate actually goes up, because now you're rebooting things that would have failed sort of later when you rebooted them. You're forcing it to happen sooner. You also have to be really careful about your coordination points, right? We expect to reboot, maybe 10 hypervisors in a data center a day. We don't expect to reboot 300 of them in a day, or 400 of them, right? So we have to actually write software that scales our systems so that it can keep up with this load of rebooting that we're going to exert. And it's really clear at this point that we are going to be investing heavily in this. We're writing new software to manage our fleet reboot. We are investigating coordination points. We're investigating performance impacts, et cetera. January 17th, we are now 16 days in. We get the first glimpses into microcode, and they reveal that we're actually going to have to do 2 reboots, not 1. Now, we're a cloud provider. People don't like it when we reboot their virtual machines. They really don't like it. And so the idea that we get a little bit of grace for doing it the first time, because nobody wants to be vulnerable to Spectre and Meltdown. But the idea that we'd have to do this twice is not very popular. Nobody really wants that. But the problem is that because of the way the microcode is at this point, it's unstable, we can't roll it out. So we're going to have to run 1 round of mitigations and then another round of mitigations plus microcode, and there's going to have to be reboots for everybody in the interim. So I know, this thing sounds like a train wreck, and it's no fun for anybody, but this is sort of the reality. And I think everybody actually went through this. It's just probably nobody's talking about it because most people just want to put it out of their brains. But we'll talk about why it's important to talk about this as well. January 26th, 25 days in, we have our first full benchmarks on most hardware. We've tracked down all the patches we need. And surprise, surprise, it's actually not any slower. Now you're like, whoa, how'd you pull that off? That's awesome. Well, we had to upgrade every part of our stack to maintain sort of a net neutral impact. So that means we upgraded all of our kernels, any drivers we used, our emulation software, our software-defined networking software, and everything that used anything had to be upgraded. Now, if you've run in large production environments, you typically don't want to do upgrades like that. Why? Why? Because you introduce chaos, you introduce changes. We don't like changes. And what we're doing here in order to keep up with these security patches is basically changing everything, because that's the only way to do it without taking a massive performance hit. Now, again, coming back to a serverless environment, to Kubernetes, to functions as a service, upgrading still requires us to do that, but it doesn't require our customer to do it too. And that's where serverless, again, starts to look really, really interesting. February 5th, T+35, this is where history diverges. So February 16th, T+46, we've now, in the real life, completed reboots in the first data center, we are 8% done with our fleet. We are averaging about 0.75% of the fleet per day. Now, let's move over to our alternate timeline. What's going on over there? Well, in our alternate timeline, we'd start with functions as a service and Kubernetes as a service, because they are the most directly attackable layers. Database as a service typically sits a couple layers back. It's probably going to be OK for now. But functions and Kubernetes are where we got to start. So we start writing automation that rolls through those and reboots them. But here's the good news for both of those. The assumption in Kubernetes as well as serverless is that you don't know when an execution unit may come or go. So therefore, we can roll through and kill them carefully without affecting the customer. So we've started doing that. And in the first couple of days, we've done 25% of the fleet because it's stateless. It's stateless. We don't have to worry about any coordinating state on any of these things. We can just kill the machine, let it come back up, and things just work. Sorry, did that move? All right. In reality, we had rebooted 11% of the fleet. We've done almost 1% per day, about 4% done in 4 days. But here's the thing. Because we're rebooting VMs, we're affecting our support queues, because we're now touching every customer we have, and we have millions of customers. So our support queues are doing this. But in the alternate universe, we've now rebooted about 60% of the functions as a service and Kubernetes as a service, and there hasn't been any customer impact. Because, again, it's built into the programming model. You don't have to think about failures in the same way you don't have to think about scaling. And we're moving at an entirely different speed. We're talking about 8% per day that we're moving through a fleet versus 1% a day. Like, that's how much faster that a well-constructed serverless environment would have let us use. And the only thing that would have really slowed us down would be trying to make sure we just keep enough capacity around for spikes. By February 26th, February 26th, we had crossed the quarter mark. 27% of the fleet had been rebooted. We are 56 days into this thing. Now remember, the other vendors in the embargo, the 5, they had 6 months to do this. And in 56 days, we were catching up with them. It was a lot of work, but we were doing it. In our alternate timeline, we're already done with our computation services. And so at this point, we've already mitigated the bulk of the attack vector, right? Like, it's going to be really hard now for someone to actually attack us with Spectre and Meltdown, because the computational side of things has already been dealt with. Now, the big thing that we still have to do in the Alterverse is we have to upgrade all the database as a service systems. And that's going to take us a lot longer, which is OK. 64 days in, we've now rebooted about 33% of the fleet in real life. And now we're starting to reboot database as a service secondaries, right? We start with the secondaries because that way, again, customers have no idea that there's going to be any sort of impact if we do it right and quickly. We just reboot the machine, and the secondary disappears for a few minutes and then catches up on the replication log, and bada bing, you're back up. Moving forward, March 9th, 67 days in. This is where things kind of got interesting for us in real life. We had 43% of the fleet done, but we had to pause. We had to stop because our customer support queues were out of hand. They were out of control. And we spent 10 days working support queues. And when I say we, I mean everybody in DO jumped in and helped out on the support queues, because we do care about our customers. And that, frankly, that's a really cool thing to me about working at DO, is that it was everybody. Like, I mean, marketing, HR, engineering, like, everybody jumped in to try and help with the queues. But here's the thing. Think about how much people power that is. Think about how many people we threw at answering questions about something that in an alternate universe, if we had a serverless environment, we would have never had to stop. And see, at this point, we're 30% of the way through rebooting DBAS secondaries in the Alterverse. It's a pretty compelling argument, right? Like, throwing a company of people at solving support queues, or you're just cruising through rebooting database secondaries. That seems like a great thing to me. April 13th, 101 days in, We have now completed 97% of our fleet in terms of reboots. But the reality is based off of my hypothetical projections, of course, we had finished all the database server reboots at day 95. So, I mean, we're moving a lot faster in this Alterverse because we have clear boundaries of state. And because we have a much more well-defined point where we know there's going to be a customer impact. And this is really where we would have seen the customer impact. We'll talk more about that in a minute. We're running low on time, I know. On the 104th day, we completed all of our reboots in real life. And let me tell you, when that email went out that we were all done, that relief, man, that was palpable. It was profound. Because we had just rolled through and rebooted 20,000 computers in about 104 days. But I should note that it took another 15 days of the support queues, of working the support queues before they returned to normal. Like, that's how much support load we generated in the process of all this. And again, this is where serverless gets real interesting. Our customers didn't need to go through that pain, right? The idea of having a virtual machine is a powerful one, and it's enabled us to do a lot of things. But serverless actually opens up some doors for a better customer experience. Now, so what? In our hypothetical world, we completed the reboots only 10 days before. Well, what did it really buy us? Was it worth all that? Thanks, Dizzy. It was a great story, and it has no point. But there is a point. Because the difference here, the really big difference, was the customer experience. In our Alterverse, in a serverless environment, we would have seen approximately 30 days of potential, not even guaranteed, potential impacts to customers. In the real world, we dealt with 70 days of guaranteed impact to every customer we had. That is a profound difference. And how did serverless make things better? Well, less customer impact by a significant amount, no dependency on the customer to also do their own mitigation. Hey, we rolled all this stuff out, right? Like, we rolled out all these mitigations. But all that meant is that the customers now have to do their own mitigation, right? We can't do that for them because they have a virtual machine that they are responsible for. So again, it's not just about scale out, it's also about scale refresh. And finally, clear boundaries of state management throughout the system meant that we could move more quickly and do it in a more precise and surgical way when we're doing these reboots. So I hope, went a little bit long here, but I hope that this story sort of paints a picture for what could be with a serverless world. Like, I know it's not super defined yet. We're still working on that. And I know there's lots of stuff for us to work on. But there is so much potential here. Not just potential for us to have cool technology, but potential to make customers' lives materially better, and potential to spend less time throwing organizations of people at solving problems and let them focus on building new things. So that is the story of Spectre and Meltdown at DigitalOcean. I'm only over by a few minutes, which I count as a great success. So thank you very much for your time. I really appreciate it.